languages have traditionally used. On the one hand, we have static typing, which has the benefits of being safe, good for documentation, and typically these languages are performant, but sometimes people criticize these languages as being inflexible or hard to understand. And on the other hand, we have dynamically typed languages that are characterized as flexible and interactive and easy to use, but typically can be a bit slow and too many errors can escape till runtime. Gradual typing has emerged as an effective way to kind of take the benefits of both of these typing disciplines and put them for one language. So instead of having programs that are entirely statically typed or dynamically typed, we can mix static and dynamic checking. And so instead of having basically one type for your program, you can have multiple possible types. So we could start with a program that's relatively statically typed and change some type annotations and move it to a more dynamic direction in case we have some kind of a type error, or if we have a program that's dynamic and we've tested and is performing well and we want to add type safety, we can move it to the more static direction. Unfortunately, trying to migrate these programs to use new types can be quite cumbersome. So basically, it can end up trying to feel like pushing a car that's stuck in the mud. As we run into type errors, we have this kind of manual difficulty, and doing this process manually and brute force is kind of inelegant. So we developed migrational typing as a way to lift your car out of the mud and basically automatically transport you to some desired typings. So just to give some basically overview of the different difficulties certain migrations have, we'll consider this Haskell-like language where we have unannotated parameters that are type inferred by default. Otherwise, we add a dynamic type annotation to have them be dynamically checked. And the question becomes, how can I remove these annotations to get the most static type possible for this program? So if I proceeded naively and removed both parameters, or both dynamic annotations and both parameters, I run into a type error because the uses of x and the branches of the condition disagree. Even expects x to be an integer, not expects it to be a Boolean. Similarly, if I naively just tried to remove dynamic annotations from left to right, I get the same type error. So then I can then check if I just remove the dynamic annotation for y, but I've already gone through these two different other type errors, and this could be quite a cumbersome process of trying something and then seeing a type error and trying something else. And similarly, there are certain difficulties when we go static to dynamic, so long as we assume that we're working with a program that has a type error. So basically, we want to take this program which has a type error and move it to a more dynamic version so that we can delay that type error and maybe test out some other function definitions. So basically, the question becomes, how do I add the least amount of dynamic annotations to get rid of this and where? So if I proceed, just based off of the error message, maybe I try and directly annotate the use of x in the application, or maybe I just kind of go through and say, hey, let me try and annotate all of the parameters and see if that removes the error, and then try and make it more static later. Or maybe I just start going in a left-to-right fashion, trying different things. Maybe I see that x is in the error message, so I annotate that with dyne to see if it gets rid of the error. And so this is an efficient way to try and migrate your program to get rid of these errors. So there was a couple of fundamental questions we wanted to answer. One, can we safely automate the migration of programs to their most static state? So can I take a program with a lot of dynamic annotations and make it as static as possible? And two, can I take a program that has a type error and add the least amount of dynamic annotations possible to remove the type error? But we're only going to focus on question one in this presentation, but question two is also covered in the full paper. So to outline a naive solution to this, we can start with our source program where we have n dynamic parameters. And basically, I can then generate 2 to the n possible migrations, as in 2 to the n target programs where we remove certain combinations of dyne annotations, pass each of these separate programs to the type checker, and then collect all of the ones that are well typed and give it to some kind of type ranking algorithm which uses the precision relation in gradual typing to find the most static ones. Unfortunately, this takes exponential time, so this doesn't scale well as we start to add a lot of dynamic parameters to our program. So I'm going to try and outline a better solution here. So if we look at our original program with 2 dynamic annotations and this new program where we've removed one of them for y, we see that there's actually a lot of the typing process that can be reused between these two. So looking at the branches here in each one, we see that both branches have the exact same typing process. X is dynamic in both the migration and the original program, and even and not always have the same type. So we don't want to basically naively keep recomputing this typing process. We want to figure out how we can share the typing process between the different possible migrations for our program. And so we're going to do this with what's called variational typing. So to give an overview of how variational typing will encode migrations, we'll start with this simple function where we have a dynamic annotation. And basically what we do is we go through each parameter with a dynamic parameter and introduce a unique choice type for it. And basically this choice type is three things. One, there's a unique choice name, so we can always have a unique choice name associated with the parameter that we're trying to migrate. Two, we have the original dynamic type on the left. So in our original program where we have a dynamic annotation, the type resides here. And three, we have a new static type for our parameter that we're going to try to migrate to. And this is, as I said, is known as variational typing, where we basically take these programs and lift them to a variational version that we type check efficiently. And so migrational typing is variational typing plus gradual typing. So to go over the different variational terminology, basically, we have the unique choice name that we introduced, as I've said already, and the left and right elements of the pair are basically called the alternatives. And we have a process that's very similar to projection on product types called selections, where we have A.1 and A.2 as selections, and this gives us the type and the corresponding alternative. So basically, when we make the A.1 selection, we produce the original program where we had the dynamic annotation for X, and when we do the A.2 selection, we get the migration where we remove the dynamic annotation, and we have the inferred type int for X in this new program. And so we could type check all of this within the variational program. Unfortunately, there's certain challenges that we have to climb over to get this to work well. So looking at this program once again, we see that we have one potential migration here where we remove the dynamic annotation for X. And our variational program, which introduces two unique choice types for our original program to reason about how we can try and migrate the parameters to new types, which encodes both the original program and the migration. And here's our new static type for X. Now, if we look at the potential migration, we see that there's a type error in this program. So if we used, the same kind of type checking algorithm that we use in the original language with our variational program, we then see that our variational program would also terminate early with a type error. This is undesirable because we need to basically find out all of these different ones that are well typed. So if something's ill typed along the way, we don't want to stop the type checking process. So as I said, we don't want the migrational type checking to terminate early. And the reason we had a type error before was because of these two branches. One way to get rid of early termination is we can introduce error types. So as we have certain judgments in our type system where we try and migrate X to use the type int, we see that we can have not X have an error type to indicate that we're going to continue the typing process, but that something went wrong along the way, and we'll keep propagating this error type throughout the typing process. And this prevents early termination, but is undesirable for a couple of reasons. The first reason being, one, we keep propagating this error type throughout the typing process. So basically, any expression that interacts with something that is ill-typed ends up being ill-typed, and so we keep kind of manually propagating this error type along, and it's inelegant. And the second thing is that we have to muddy up the definition of the gradual type system we're working with to work with this error type. So things like the consistency relation and other things have to be extended, and it's very inelegant. So instead, what we want to do is we're going to try to constrain the accuracy of the judgments in our migrational type system. So basically, before where we had this not X having an error type, because we're trying to migrate X to this integer type, we're going to have a new form of judgment with these things we call typing patterns. And so now we're actually going to directly produce the codomain of not as the type for not X, even though there's a type error. And we're going to have these different patterns. So in things that were a well-typed judgment, we're going to decorate them with top, which just says that things look as usual. Otherwise, for judgments where something fishy would happen, and this wouldn't be a regular judgment in a type system, we're going to decorate it with a bottom. So basically, we get these two forms. One with top, where we can read these judgments as, hey, these are sound, reliable judgments in some type system. And another one where we have this bottom, which says, hey, this judgment is unreliable, something fishy what happened, and this program should have a type error. And so to get examples of these kinds of judgments, the ones with top look exactly as you expect. So we have one as type int, true as type bool, not true as type bool. This is all very standard. Bottom is where we start to get these very weird looking type ints that are nonsensical. So we can do things like one has type bool, or true as type int, or not true as type bool if we need these types to continue the typing process, but we still want to know that something fishy went on and that we can't trust these judgments. And so we can use these both with variational types. So as we're trying to reason about the judgment even X having type bool for our different migrations, we can assign this judgment top. And the reason is that when we do a selection on the selection A.1, then we have X with type dyn, even X having type bool makes sense. And similarly, when we do the selection A.2, x having type int makes sense with even. So this is completely well typed, so we can use a top here. However, when we try and type not x with type bool, we see that there's an error because when we try and migrate x to use the integer type, then there's an error here. So we use bottom as a way to let us know that these things are, this migration couldn't happen. Unfortunately, that just let us know that something went wrong with the migration, but it didn't let us know where. So we don't know why or where things were going wrong. So if we look at different selections on A, let's try and reason about just the regular judgments. So when x has type dyn, not x having type bool makes sense. There's no type error in this program. So we should have a top with this program. However, when we do migrate x to have type int, there is a type error, so we have to use this with bottom. So looking at the selection process, if we try and invert this top and bottom back into A, we come up with these things called choice patterns. And basically with this, we have a more fine-grained notion of where these type errors are happening. So in the migration where we're leaving x annotated with a dynamic annotation and it has type dyn, not x having type bool makes sense. However, when we select A.2, we also select A.2 on the type and the pattern. We have x having type int in our migration, so we need a bottom to indicate that there's a type error in this program and we can't trust what's going on in this migration. And so there's certain properties we wanted for our migrational typing, and this is just the general form of our judgments where we have pi as the meta variable for our typing pattern and m for our migrational types. And so we have certain desired properties for a typing pattern. One is soundness, as in we want no top with an error or with a judgment that doesn't make sense. So we don't want judgments like this where we're trying to migrate x to have type int and not x having type bool. So we can never have a top here. It has to have a bottom. And similarly, we want accuracy. We can always use bottom with anything to make nonsensical typings, but if we have a migration, for example, x having type bool as our migration, then we don't want to have a bottom here. We want a top to precisely indicate that, hey, this migration was okay. And then we also have desired properties for our migrational type. One is precision. We don't want unnecessary dynes where we could have had static types. And two is generality. We want gradual polymorphism. And so now I'm going to go over with this migrational typing in hand, how we can use this to find the most static migrations for our program, which was our fundamental question 1 from earlier. And we do this by analyzing the typing pattern that is the most sound and accurate one used in typing a program. So we have some program E with this choice type here that was introduced by trying to migrate some parameter. And if we have a bottom, then this program always has an error, so we can't do anything with it. So this isn't very interesting. And then our first kind of interesting thing is we could have had A of bottom top, but this can't happen due to the gradual guarantee. Basically, there's no case where a parameter or a variable has a static type and the program is well typed, but making it dynamic gives us a type error. So we never have patterns of this form in our judgments. So our first interesting case is this then, where we have A of top bottom. So this just indicates that we can't migrate the program to, the parameter to use type int, and the program also can't migrate to int. So this just indicates that we have to leave things dynamic. And finally, when we have top, this indicates that we can migrate to int. So if we look at the last two cases and we ignore the bottom one where we couldn't do anything, basically the choices that are present in the typing pattern for our judgments indicate whether or not we can migrate things. So basically when we see an A in our typing pattern, we can't migrate. However, when we just see top, then we're free to migrate the parameter that was associated with A. So to give a more, this example I've been going over, trying to find the most static migration for it, we would have this typing pattern associated with it, and we would have these different choice types where we try to migrate x to have type int or y to try to have type bool, and we have an A of top bottom. So as I said in the last slide, we have an A here. This indicates that we can't migrate x because A was the unique choice type that was associated with it. However, there's no B. So this indicates that we're free to migrate y to bool because no B in the pattern indicates that this parameter didn't affect the well-typedness of the program. So we can migrate y, but not x. And so you might be wondering, where are these types and the right alternatives coming from? I'm just kind of manually putting this int and bool here. But I don't know where they come from. So these just come from type inference. So we use type inference to find these types we're trying to migrate to. And if you want full details about this, you can see section 7 and 8 of our full paper about constraint generation and constraint solving. And to summarize basically what we've done, for each dynamic parameter, we introduced a unique choice type to reason about how we can get rid of these dynamic annotations. We then migrationally type the program and produce a valid typing pattern that is as precise as possible. And then we search this typing pattern for top and unused choice names to see which parameters we were free to migrate towards new static types. And if you want to see some more details about this, we have the full migrational type system and the algorithms for searching these patterns in the full paper. And the thing is, as I said earlier, that we wanted to do better than the naive approach. So we basically measured how well we did as program size increases. And we see that the brute force naive approach, as the number of function definitions and number of parameters, if we get 150 dynamic parameters on only 250 lines of code, our brute force approach starts timing out at about 1,000 seconds. However, migrational typing performs quite well. So gradual typing, doesn't take long for these programs. For just gradual typing, the original program we're trying to migrate, we are only doing 2 to 4 times the slowdown, basically finding all of these different migrations, type checking them, finding which ones are valid, and then finding the most static migrations. So we did this very surprisingly efficiently. And so our major results are that we could find all migrations for a program and basically get to any of them. We can then search these for the most static migrations and find them efficiently. And we do all of this with marginal performance overhead. So to summarize, basically we had these programs that were stuck in the mud that we didn't know how the hell to change the annotations for. And we went through and we saw, oh, there's some function with a dynamic annotation. We introduced a unique choice type and an inferred type on the right that we're going to try and migrate to. Then we migrationally typed the program and produced a typing pattern like top, which indicated, hey, we're free to migrate the parameter of double x to have type int. We saw that then this was the most static migration and automatically migrated the program so that we got rid of this dyne annotation and that this function had type int to int. So basically we automatically lifted this program to a desired most static typing and eased the burden from the user to a tool. That's it.
Hi, really nice talk. So it's interesting you mentioned that you're doing type inference, because my question was related to that. So for example, so when you have constraints and you're just adding constraints to the system, and eventually you're going to solve them, that's more or less well understood. But sometimes when you have systems that inherently have choice, for example, when you're checking union types as you're doing inference, you have a very similar problem where you do not know which branch to check against. So, and you don't know what kind of constraints to add to your system. It introduces an inherent kind of disjunction in your constraint system. So I was wondering whether the inference you do are just limited to inferring the static part, or do the things that you infer also could they also be making choices?
So basically in the presentation here, we were limited to static types on the right. However, in certain migrations, there was actually basically ways you can migrate to different static types depending on how other things were dynamic, and it could still be well typed. Right. So that we did have a way to infer different ones. I haven't looked for, basically we're working with a language with full and complete type inference underlying it. So we didn't have difficult language constructs for inference, so I don't know how well our system would handle that, but I think we could still do a lot, I guess.
Okay, thanks.
Hi, Nate Work. You might have just answered my question, but just to clarify, does there always exist a most static typing, or is there some notion of like really precise maximality? Or
right. So it's there's more than one most static migration essentially. This is the difference between maximum and maximal, I guess. Yeah. So yes, there could be certain cases where, because precision is a partial order on gradual types, that we added a dyne here and made a static type somewhere else, and vice versa. So we just find all of the ones that basically you couldn't make them any more static without getting an error, and there's more than one of these. And yeah, so there's different ways you can kind of rank how you want to recommend a most static migration in our system. So maybe you want one of those that removes the most amount of dynes. And so that might be one way, but there's other criteria you could use.
Okay, thanks.
Yeah.
And my second question was, your examples here are showing primarily adding ascriptions to type variables rather than having ascriptions on expressions.
Correct.
Did you look at programs where you kind of fully translated like Seek or others to like a completely dynamic program as opposed to just annotating variables in a program?
So I think with the evaluation, we only did annotations of the formal parameters, but we have the construction. You can add arbitrary dynamic ascriptions, and our approach still works fine. And moreover, you don't have to just use dyne for parameters. You could say like this is dyne to dyne if you wanted a function type whose domain and codomain were dynamic, and we handle that as well. And you can remove one of the dynes from the codomain or the domain, and we can migrate those two.
Okay, thanks.
No problem.
Hey, I had a question about when you have dependence between two dynamic variables. Mm-hmm. Is that essentially worst casing back at the naive case because you kind of just have to combinatorially apply them, or how does that?
Yeah, well, yeah, there are certain cases where if you have two dynamic variables interacting, then they're just dynamic. However, if you try and migrate one to a static type, then, for example, if it only interacts with that other variable that's that dynamic, then we would say that there's like a type variable for that, and that would be gradual polymorphism. But I guess I don't quite understand what you're asking.
So if I have like a dynamic function, like x applied to y, or something like that, and we might be able to apply a static type to y, but maybe not to x, or maybe there is one, but does that just become exponential like the naive case, or is there ways to make that faster?
No, there's ways you can make it faster. So basically we would go through and search like an x applied to y, x would get some kind of, you're migrating it to static, some kind of function type, and then if you would just do y, then you wouldn't have much you could do. But anyway, no, we can do this pretty efficiently. It's not this huge explosion, but some cases are kind of pathological.
Okay, thanks.
All right, so could you say a little bit more about the type inference and how it relates to prior work on type inference and gradual typing? So, for again, compared to like Ronald Garcia's work and Matteo Cimini's and.
Right. So we built on Ronald Garcia's work. In fact, so our underlying language was ITGL. So basically, we took that, and where he would just have some type variable that was associated with an unannotated parameter, or you would just have a dyne there, and that would be the end of it. You would just try and use that type variable to unify things. We would then try and instantiate a new type variable for the dynamic one as the right alternative of the choice type we introduce. And then basically all of the constraints, once we get rid of the variational stuff we're doing, goes to all of his properties from his paper.
Okay, cool.
Yeah.
Great, thanks.
No problem.
We have a question from the internet.
Okay.
Can you have more than two choices for your type, and also can you compose?
No, so each. Wait, what? Oh, I'm sorry. So they asked if basically we could have two choices. More. Okay, right. And also, what was the other question? And we could compose them. So no, not really. So each type basically introduces a choice type. What ends up happening is, for example, the right alternative, which is a type variable when we're doing this like algorithmically, when it interacts with something that's also trying to migrate and has a choice type, that choice type gets nested within. So you end up kind of having, like for these migrations, a bunch of choice types nesting. And this will let you know as you're trying to change the types for these parameters. Maybe if like something else was left dynamic, you have this type, and then another case you might have another type. So these nesting occurs where you have like 2 to the n possible types, but not always. Usually we kind of can break down these choice types to less than that. Whereas you have like 2 dynamic alternatives within one choice type, then we just say, oh, this is just dynamic no matter what. So we collapse that. But yes, so basically when you start nesting these, then you reason about the different possible types you could have for your parameter, depending on its uses.